Okay, so to wrap up today's lesson, let's also address, so remember at the beginning of the class, we said, we showed you how to do adding forces in one dimension, and it's pretty simple. And then we showed you how to do it in 2D, which seems like a whole different method. So I just want to comment on connecting the two and show you it's not so different. It's really the same method, but it's just that there's a simpler way to do it in one dimension. So let's see how do we find net forces in one dimension again, right? Remember we started with that example. If A is pushing to the right, so we have a pushing force by A with 10 newtons and pushing force by B, which is pushing to the left like that. And we just simply take PA, the magnitude of PA, and subtract by that. How do we reconcile with the fact that this is our formula? In vector, when we add a vector sign, remember I made a big deal of without a vector, it's a magnitude, because with a vector, you will always use add. You never use, or very rarely use subtract, okay? And how would that work? How does that reconcile with each other? Let's think about it, right? So what is PA? PA vector, let's write it in component form. Let's write it in IJK, right? Because I don't really have different components over here. So let's write it in IJK, it kind of makes a little bit more sense. So the magnitude is 10. Let's forget about the units in a moment. And in the positive I direction, right? And PB as a vector is 5 in the negative direction. So it's minus 5I, right? Agree? So let's add these two together, right? And again, which one's positive, which one's negative? It's because I'm defining the positive x direction to the right. And now PA is 10I plus PB, right? So that's PA, 10I is minus 5I. So 10I minus 5I, how many i's do you have? Well, 5I. Like this. So you see, I could write it like this, and that's done. So you get the same answer, but this is in vector form. Let me put it in a box, right? Or you can write it like this, and this is in the magnitude direction form. So this is the magnitude, this is the direction, right? So it's actually the exact same thing. In one dimension, it's almost trivial. Technically, you need to always give your answer in magnitude and direction. But yeah, so if you need to extract this out, it's very simple. You can see the magnitude is 5 if you want to make sure you get the credits, right? And put in the units, and the direction, that the fact that it's positive I hat means that it's going to the right. Okay, so as you can see, both methods work. Now, it also is particularly useful if, what did I do? I switched the two, right? So I made this one a little bit longer, like this, and made these shorter. So if that one is 5 newtons and that one is 10, what did I do before? Well, before I said well, let's see how do we do it in the full on proper method first. So remember I said this is always addition in the vector way, right? However, PA and PB are going to be different, right? So PA is going to be 5 units to the right, and PB is going to be negative 10 units, right? It's going to the left. So it's negative 10I. Remember, I is pointing that way, but negative I is pointing the other way, and it's 10 units to negative. So now you see all the vector, unit vector and base vector concepts all come together, right? So how would you plug this in? Well, that's 5I. I'm putting in extra parentheses to make it extra clear, minus 10I. So what do you get? Well, you get 5I minus 10I is minus 5I, right? Again, you can put in your units. Of course, that's not the right answer over here. We'll see how we can match this up, right? So, and you can also see if this is a vector, this is a vector on both sides must match, right? So I'll put this in a box, and you can extract out what's the magnitude of this vector. Don't put minus 5 because magnitude is the length of an arrow, and length cannot be negative, right? What does -1 centimeter means? So if I ask you what's the length of this marker, and you cannot say it's -5, a length is always positive, right? So the length is 5, so the magnitude is just 5 newtons. But the direction, because of the negative sign, we understand it's to the left. So you need to use a little bit of common sense to extract out, well, read this and it should hopefully be obvious. How do you know what is positive or negative? Because I should say, it's always pointing to that way, okay? So this is how you would give your full answer, right? Magnitude and direction. Couple of comments, you also see that this is why magnitudes are sometimes written like this, right? With like the absolute value sign, we borrow the same notation from just algebra for magnitudes of arrows, magnitudes of vectors, because it's always positive. Magnitudes are always positive. So it's almost like taking an absolute value, but of course, there's a little bit more than that. You get rid of the vector part, right? So be very careful. No vector sign here. So scalar equals scalar, vector equals vector. Yeah. So remember, yeah, that's a scalar, but scalar times vector is still vector, right? Remember scale multiply, right? Yeah. Now that's connected to the old way, or the first way I showed you, is I go like, just look, don't worry so much, because in one dimension, you don't really need this heavy machinery. So that's why there's a quick way of dealing with finding net forces. If everything is just in one dimension, it's always simpler, right? So in one dimension, the net force, well, I said the easy way is just take whatever's larger and subtract whatever is smaller, right? So 10 minus 5, all right, 5 newtons. And then use your common sense to think, well, which way would the net force go? Well, the net force would probably, this is much larger, so it will be to the left. And now you have both the magnitude and the direction, and you can double check, have the exact same answer. So this is the connection between the two frameworks. This is the always work in, no matter how many dimensions, even in 3 dimensions or 4 dimensions or whatever, it will always work. That is a quick way to do one dimension. Quick comment is, if in one dimension, if you have a lot of forces and it starts to get confusing, you can also use this method as well. But if you can get away with doing with vectors, you can always just deal with scalars. Notice there's no vectors at all in my steps over here, and it looks much simpler. All right, so you have understand all the connections together. So let's just summarize where we are at. So this wraps up this lecture. So in this chapter, or in the last chapter, we understand what are forces. We know that it's a push or a pull. It's a vector quantity. There's magnitude and direction. We know the different types of forces. Where we look at a couple ones like a driving force, a pushing force, different things over here. And we understand how to use free body diagrams to analyze all the forces on an object. And this lesson was focused on how do we add up the net effect or the resultant effect or the total effect, right? These words are all equivalent of the scenario. Okay, so where is this going? So next lecture and next week we will look at how will these net, once we have a net force, so we'll have lots of force acting. When you stand here, when you're sitting here watching this video, there's lots of forces acting on your body. So once you find the net force, how does that affect different types of motion? So we'll look at that in the next lecture. So this will already give you plenty of things to practice. So make sure you can do these type of problems over the weekend, and the more you practice, hopefully the more comfortable you'll be with them. Okay, all right, I'll see you guys in the next lecture.